Good afternoon, students. You are welcome to Physics for Integrated Science SED 123. Today's topic is Newton's laws of motion. Newton's laws of motion is very important because it forms the foundation of classical mechanics, one of the branches of physics. Mechanics is the study of how objects move or do not move when forces act upon them. I am Dr. Akpata, your facilitator. Thank you. Good afternoon, students. You are welcome. Students, you are welcome to Newton's laws of motion. I am Dr. Akpata, as I've said, I'm your facilitator. Today we'll be touching the first law of motion, the second law of motion, and the third law of motion. At the end of this lecture, you are expected to be able to state and explain the three laws of motion as expanded by Newton. Also, you'll be able to apply the derived formula to solve problems. Now, let's start with Newton's laws of motion. The first law states that every object continues in its state of rest or of uniform motion in a straight line unless acted upon by an external force. If you can see the screen I'm sharing with you now, we have balls here. We have one ball at rest. What the law is saying is that this ball that is at rest, if you don't push it, that is, if you don't apply any force on it, the ball will continue to be at rest till eternity. From now till infinity, that ball will still be on that same position. But by adventure, if you can just give it a push, you'll find out that this ball will continue rolling and rolling and rolling and rolling, except if it comes across an obstacle that stops it from moving. So what the law is saying in essence is that when an object continues to be in a state of rest, that object will be there. It will not move, except if an external force just acts on it. That is, if something just push it. When something push it, that ball will begin to move. And as the ball is rolling, is moving, if you don't stop it, if there's no obstacle along its way, that ball will continue to roll from here till infinity. That is what the law is saying. So we call this law the law of inertia. That is, there is reluctance when you are in a state of rest. You don't want to move. There is this reluctance. And the same thing is when you experience if you are in a moving car. If you are in a moving car because your body particle is moving along with that car, that is a motion. Peradventure, if the driver applies the brake, there will be jerk, you jerk backward because you don't want to stop. You want to continue moving along with that moving vehicle. And when vehicle is at rest, you are inside that vehicle. That vehicle you board, it happens that the driver just kick the car and start moving. There will be reluctancy because your body is already in that state of rest. You move, jerk backward. You don't want, before you now adapt yourself to that motion. and accept the same thing happen when a car is in motion. Your body particle, they've like adapted themselves to that motion, forward motion. So if there is sudden application of brake to now stop, your body will first of all move forward because you are in that forward position. You've adapted yourself then before you now come back. So we call this reluctancy. That we call this reluctance, and we call it inertia. That is, you are reluctant to stop moving, or you are already in a state of rest. You don't want to move. So we call it laws of inertia. So this next one is second law of motion. The law states that the rate of change of momentum. What is momentum? The rate of change of momentum. Momentum is just the product of mass and velocity. When you multiply mass of a body with the velocity attained by that body, you'll be talking about the momentum of that object, of that body. So the law is saying, that the rate of change of momentum is proportional to the impressed force and takes place in the direction of force. If you look at my screen, I have force is equal to mass times acceleration. And you remember in the last lesson, I taught you that acceleration is change in velocity all over time. Acceleration is change in velocity all over time. So you will now follow. I want you to, moving on, you'll be able to see how we are able to derive force is equal to ma from this second law, which states that the rate of change of momentum is proportional to the impressed force and take place in the direction of the force. Look at this. You know, I told you that the product of mass and velocity is called momentum. That is mass times. When I mention product, I'm just putting multiplication sign there. When you multiply mass with velocity, the answer you have is momentum. This is your activity 1. I would like you to apply the previous formula, which is for mass times velocity to form momentum, get momentum. I want you to use it to solve this problem, this simple problem, very, very simple. Let us look at the activity together. The question says a ball of mass 5 kilograms has a velocity of 2 meters per second. Calculate the momentum. Remember, I told you that momentum, the formula for momentum is mass times velocity. Now, if you have to, you first of all bring out the parameters we have in the question. We have mass of that ball to be 5 kilograms. Then we have velocity to be 2 meters per second. Now, calculate the momentum. You should be able to do this, students. We are back to the Newton's second law of motion, which says that the rate of change of momentum is proportional to the impressed force. So, you know, I told you that momentum is simply mass times velocity. So we have force, which is proportional to mass times velocity all over time. Force is proportional to mass times velocity all over time. I'm sure you remember that in your secondary school, you were taught that if you change proportionality sign to equality sign, you must introduce a constant. Constant will come in. So it's because we are changing this proportionality sign to equality sign. That's why this K, constant, is coming in. And the value of this constant is 1. So you can say force is equal to mass times velocity all over time. Remember that acceleration is velocity, change in velocity all over time. Acceleration is change in velocity all over time. So we can say force equals mass times velocity all over time. This velocity all over time is now standing for acceleration. So remember that in the previous slide, I told you that force is equal to mass times acceleration, because velocity all over time is acceleration. So force equals mass times acceleration. This formula is just showing you the mathematical way of expressing Newton's second law of motion. Force is proportional to change in momentum all over time taken for the change. So mathematically, we have F to be proportional to mv. That v is the final velocity, while the u you have in the formula is standing for the initial velocity. So the difference between the momentum, initial momentum, and the final momentum all over t. So we have force, as I've said. Remember that what we want to derive from here is that we want to know how force is equal to mass times acceleration. And we are deriving this one from the Newton's second law of motion, which says that the rate of momentum is proportional to the force, to the impressed force. So now from this final momentum minus initial momentum all over time, we were able to know that force is proportional to mass into final velocity minus initial velocity all over t. Remember that velocity all over t is acceleration. So that means we are going to substitute acceleration for change in velocity all over time. And from there, we are able to have the formula for force to be ma. ma. We have F proportional to ma. I told you that in your secondary school, you were taught that when you change proportionality sign to equality sign, you must introduce a constant. And the value of this constant is 1. So if value of constant is 1, so we come to force equals ma, which is mass times acceleration. So this is your second activity. Calculate the acceleration if an unbalanced force of 40 Newton acts on a 4.0 kilogram block. Look at the question. Look at the solution provided for it. So our acceleration will now be 10 Newton per kilogram. 10 Newton per kilogram. From how are we able to find this acceleration? Remember that force is equal to mass times acceleration. The question is asking for acceleration. So all you just need to do is to make acceleration the subject of the formula. From this formula, force is equal to mass times acceleration. So by the time you divide the two sides of the equation by force, by mass, we have force is equal to mass times. Force is equal to mass times acceleration. Divide the two sides of the equation by mass. Force all over mass, mass times acceleration all over mass. So mass and mass will cancel each other. You are left with acceleration. So acceleration will now be force all over mass. Our force from the question, from the data we are given in the question is 40 Newton. While mass is 4 kilograms. So your answer for acceleration is 40 Newton per kilogram. This is the second activity for you. I want you to solve this. I provided that data for you. So from the data, look at it and solve it for me. The question says a ball of mass is 0.6 kilogram moving at a velocity of 20 meters per second is suddenly hit by a force of 5 Newton. So solve that question. Now coming to the Newton's third law of motion. This third law of motion states that action and reaction are equal and opposite. What are we saying? Action and reaction are equal and opposite. I'm going to use one illustration for you. Assuming you have a chair that is not so strong, and you now happen to sit on that chair will crash. That shows that the action you are putting on that chair is greater than the reaction the chair is giving to you. And because of that, that chair could not support your weight. So the chair will crash. Assuming you are sitting on a chair that has a reaction that is greater than your own action, what will happen is that that chair will throw you up. But this law is saying that for any to have a balance, action must be equal to reaction. That means if you are able to sit on a chair comfortably, the action you are putting on that chair and the reaction the chair is giving to you in the opposite direction is equal. And because of that, you are able to sit comfortably on that chair. That chair did not throw you up, neither were you able to crash the chair. So with this one, we come to the end of the third law of motion. This one I'm showing to you is your class activity. How can Newton's third law of motion find application in your environment? Apart from the one I've cited, I want you to give me how Newton's third law of motion can find application in your environment. On this note, we come to the end of this lecture.